Okay, I can also hear you. Let me just set this thing up first. Uh, okay. So thank you for confirming that the system is working. Now again, I think I should be starting very soon. Can I check with you? If there are any questions from anyone? No? Okay. Just a quick uh, announcement. As you can see, next week, no, week after is a public holiday. I think 2 weeks from now. But so the replacement will be on next Wednesday. So for the 2 tutorials that are seen on the screen involving the REE and the RMH students, Group 3 and Group 1. The link, the Google Meet is as usual. So you use like the same Google Meet for the tutorial. And then for the last class RMH, I think we'll have to probably, maybe not. So for the lectures next week, this time, there might be a slight delay in case I cannot finish it on the other side. That means the tutorial with RMH 4. So let's get started. So if there are no questions, I will continue. Now, where were we? Right? Let's see. So a quick recap. Last week, we started on this topic of artificial neural networks. Hang on. I should adjust this one. Okay. So just a quick recap. What did we learn? So we talk about the. Oh, okay. I seem to have left the. Okay. We talk about. We basically look at the motivation. Why we wanted to look at artificial neural networks. So we look at what are we good at compared to what machines are good at. So basically, you can see we always try to leverage on what the machines are good at, so that we can produce a super human being in a way. Because we're talking about replicating, copying what the humans are good at in a machine. Because what the humans are good at, for example, would be in terms of creativity, in terms of recognizing images, recognizing scenes, pictures, and then also we are able to recognize things quite well. So there's one part we wanted to copy. That was part of the motivation of artificial neural networks. And of course, because human beings have limitations in terms of what we cannot work for 24 hours a day, right? So machine can do it. So we are also continuing in the same discussion of expert systems in a way. So expert here now, I think we will probably look at it in terms of a more modern term, which is instead of calling it expert system, we call it intelligent systems. So then we move on to look at some of the common architecture and what are the characteristics of your artificial neural networks. And then I think later today, we go on to the next part, which is the evolution of artificial neural networks and some of the key developments and some of the key people that actually contributed to this, I think more than 50 years of history of the technology. So it's not like was discovered yesterday. And I see that you bring in lots of different ideas. And some of this actually is evolving now, even as we speak today. Somewhere in this world will probably be trying to improve it, right? So that is or maybe look at maybe other things to actually improve the artificial network or coming up with a new system that can also be better maybe than the existing systems today. So that is the, in a way, history of the human development. The last part here, hopefully we can cover it today, is on the perceptron learning rule. So we look at one of the rules, which is the perceptron learning rule, and see how we can use it to actually train your simple artificial neural network based on the perceptron. Okay, that was why we were. So now we go back to, maybe stop. Okay, so let's look at some of the types of artificial neural networks. Now, regardless of whether it's a deep or a shallow artificial neural network, as you see later on, there are some, I would say, some differences between the shallow and the deep, but of course it is more in terms of the architecture. So this is some of the basic, as I said, basic types of artificial neural networks. We have what we call the first type, the first class. So what we call the feed-forward neural networks. The name itself will become very clear later on in the next few slides, why we call it feed-forward and not anything else. So feed-forward neural networks, of course, there are many types, but I think the three, some of the more major ones will be the perceptron, which is basically a single neuron. So a single neuron can also do interesting things for these artificial neural networks. Then, because of the limitations of your perceptron, we then have a multi-layer neural networks, right? So they're multi-layers. And I think after that, then there was also evolution in movement in or work in a different direction to improve it. So you have this self-organizing network named after the what do you call it? Named after the inventor, if you like. So the inventor is Professor Kohonen. Right? Kohonen actually discovered or proposed this self-organizing network. Then, of course, as I said, there are many, many more. So now, this is one class which is the feed-forward. There's also another class which is your recurrent neural networks. So what are the differences between the recurrent and your feed-forward? So we will spend some time looking at the recurrent neural networks, in particular the Johnhoffield net. There'll be much more. There'll be many more different types of recurrent neural networks, and of course those will be much more complicated. So we just touch on one example of the recurrent neural networks, and it's quite simple to understand. Once you understand that, it is hope that you can also understand and appreciate the other variations of your recurrent neural networks. Now, what are feed-forward neural networks? Basically, if you look at the first class, your feed-forward, it is an artificial neural network where the connections between the units, the processors, do not form a directed cycle. Now, what's a directed cycle? A directed cycle, also known as your a path to a net, following the direction of the arrows. So that will be your what you call a directed cycle. So and because of this feed-forward, right? It doesn't. There's no the connections. The connections between them do not form a directed cycle. So more importantly, or in simple terms, if you look at later on, you look at the feed-forward neural networks, you find that the information always moves in one direction. It never goes backwards. There's no feedback. So now, hopefully, you can see why we call it feed-forward. Because feed-forward, you move in one direction and it's always forward. It never goes backwards. There's no feedback, or there are no feedbacks. On the other hand, your recurrent neural nets is a class of neural network where the connections now between your units form a directed cycle. So basically, that there is some feedback. There are feedbacks. So this, because of this, uh, the connections which form directed cycles, it creates an internal state of the network which allows it to exhibit dynamic temporal behavior. Of course, you look at it. Why do we want to go into having such recurrent neural networks? Because it can do certain things that the first type, the first class or feed forward cannot do. Therefore, we have this someone invented or someone proposed these recurrent neural networks. Now, both types also have deep learning. Also have what I call that. They are also involved in deep learning neural network architectures. So they are. So again, you will see later on. Now, connectionists, basically people working in the area of artificial neural networks, agree that recurrent neural networks, that is, networks wherein the connections of the network can form a directed cycle, are a better model of the brain than your feed-forward neural networks. So that's why I think we have said in the beginning, at some point you see that some of the architectures do not closely resemble, do not closely imitate, or they are not similar, right, to what the actual architecture in our brains are, right? But they are still loosely called artificial neural networks because they are because our brains have feedbacks. In this case, this is actually a diversion, though it's not following the biological way of um, creating the neural network. But they agree that this one, the second one, is more closely, right? It's closer to the actual brain. But the first type, the feed forward, can still do interesting things for computing purposes. Right? So you have your feed forward and your recurrent neural networks. So now, after having a glimpse, having some idea of the types of the classes of neural networks, let's look at some of the basic features. Now, again, we talk about basic features. Let's only look at two. Let's look at it in terms of your architecture, and then look at how the networks learn. That is your types of learning rules for your uh, neural networks. So this is actually one type here. That is, I can see here. Basically it's a feed forward, right? So these are the neurons. I can see the information going from the bottom to the top. So these are the output neurons here. So of course there's a one middle layer here. So this is one example of so your input goes to the output. So in the second type, then this type here actually have, I can see here, there are feedbacks. This is your directed cycle. So feedback from the output to the inputs, and then it connect to all the other, feedback to every single neuron. So you can now begin to imagine, there's a lot of connections going on. And of course, as a result of that, there's a lot of calculations that you need to do. Other than that, we also have other types whereby the outputs talk to each other. The outputs talk to each other by having feedbacks on the outputs, right? But in the earlier two cases, this one and this one, the outputs here do not talk to each other, right? And this is multi-layered, right? Depending on how many layers you want. And of course, this one is a single layer, right? As you'll see later on. So such examples will be your Johnhoffield net. So we talk about architecture. Now let's look at the types of architecture. I've shown here some examples. I can see there's quite a large number, right? You have your art. Now, when those of you who are doing some work on using artificial neural networks, especially in your literature review for your FYP, you may come across the names, some of these names. For example, adaptive resonance theory nets, or ART for short, art nets. This was actually proposed many years ago by Gil Carpenter. Then the neocognitron. I think neocognitron was proposed by Professor Fukushima. And Professor Fukushima actually, I think I saw before some people actually said he's actually the father also, father of deep learning. So Fukushima, and then he was the one who looked at who proposed the neocoordinatron. Now we also spent some time later on in the this morning to look at what is so special about your neocoordinatron. Then there's also unsupervised projection pursuit neural networks. Then I've said just now, I said before, the self-organizing maps or self-organizing neural networks, or SOM for short, proposed by Professor Teivo Kohonen. Then, of course, you have your very famous, if I may say so, famous as in, every time you look at neural networks, you can't run away from multi-layer perceptron, or MLP for short. And that was proposed by the group of Rosenblatt and McClellan. Again, many, many years ago, I think probably in the 90s. Then we also spent some time to look at one example of the recurrent nets, which is the Johnhoffield nets. As the name suggests, this was proposed by Professor Hoffield, Johnhoffield. Actually, he plays a major role. As you see later on, he plays a major role in actually reviving the field of neural networks. Then going in a different direction was the bidirectional associative memories. Now, the Hopfield net, as you see later on, actually has one peculiar, interesting function. It can serve as an associative memory. Later on, we see what you mean by that. But then this to improve it further, Professor Bart Costco proposed the bidirectional associative memories, which is supposedly better than the single direction Hopfield nets. So you can see here, we can actually spend the whole semester looking at just artificial neural networks. There's so much to know and to learn, right? Of course, we don't have that luxury of such time. We only have probably 2 topics, or 2.5 topics, including your deep learning, before we have to move away to go to look into other areas of artificial intelligence. Now, the capacity to learn is one of those things, one of those advantages, a strength, something unique strength of your artificial neural network, which is ability to learn. Right. In the earlier 2 cases, we look at expert systems in terms of the Bayesian method, which is basically based on statistics, and also your certainty factors, as well as the fuzzy logic. It's not able to learn, right? So you have to actually create the rules yourself to actually force the system to do something useful. But in the case of artificial networks, one of its strengths, that's why it's so popular, is able to learn. I don't have to create the rules, but the system is able to learn. So neural networks can recognize patterns and analyze subjective information. Subjective, what do you mean by subjective? For those of you who may not know this, basically, it means that if I give you a picture, okay, I give you a word, apple. I like apple. Right? I think I've given the example before. In a way, it's quite subjective, right? What do you mean I like apple, right? Apple means apple the brand, or apple the fruit, right? So things like that, subjective, subjective. But neural networks can help you to do that without telling it what it's supposed to mean. It will tell you as long as you show it enough patterns, enough examples for it to learn. Right? So it learns by keep repeating the same thing. Right, so same thing like human beings. If you want to remember a certain formula, you have to keep repeating it until, or practice it in your tutorial, your own time. You keep practicing until the memory is stored in your brain or in our brain. So that's by learning by examples. So artificial neural networks learn by gathering and storing information from the computer user. So you input the information for it to learn. Now, on the other hand, when the neural network receives new information, its users is stored expertise. That is your knowledge database, right? Your knowledge base, or expertise. We call it expertise now. Remember we talked about this architecture before in the earlier lectures on the expert system architecture. You have your rules, your knowledge base, and your database. Database in that example was actually based on the actual incoming data coming from the sensors, real time. But the knowledge is the one you keep all the rules. In this case, this is your expertise. So when the neural network sees receive a new piece of information, it then compares it. It uses its stored expertise to classify or recognize the pattern in the new information. If you were to show the neural network after it's been trained, it will then you ask it what is supposed to be. So it will then compare. It will compare or uses it will uh, assess is stored information in the database, in your knowledge base, and see what this is supposed to mean. So we then recognize and tell you what this is supposed to be. So generally learning. So again, in general, neural nets can learn by examples. Very important. I learn by examples. So they need to give it enough examples to learn. Neural networks also have the ability to generalize. Now, later on, we'll talk about this in the next few slides. What do you mean by generalize, right? Not here. Later on. So learning rules. Now, when we talk about that was on the architectures. Now we go into the types of learning rules that is commonly used with some effectiveness, with some good results for the neural networks. For example, there's a backpropagation. We'll spend some time looking at this in more details in the next few lectures. And there's the other types, radial basis function learning, fuzzy gated training. Basically, it's a combination of fuzzy into your learning algorithm. Of course, there are many. Of course, the latest one will be deep learning. Now, what do you mean by generalization? What is generalization? So in this example, you can see here, I have this example of training patterns. As you can see, all of us can see, it is basically number 4, right? Number 4. But notice that these numbers here are not written in the same style. So because it's not written in the same style, how can you write a computer program to recognize it without using neural networks? So in the old days, it's very difficult because for us to actually, to hard code write a program to recognize number 4, but someone will then write number 4 in a different way. So how can you get your computer program to actually cater for all these different styles of writing number 4? So this is your, so in 1988, Professor Fukushima proposed his neocognitron, able to recognize these patterns, right? After being trained, after you train your system, before training the neocognitron with these numbers, with these pictures, the network, the trained neocognitron was able to recognize new and almost similar patterns. So that was the what I call interesting fact, and also the attractiveness of your neocognitron. So here we have 7 patterns to train your network. So now the network was the trained network was able to recognize these test patterns. What do you see? The first one here consists of some noise, right? As represented by these points. At the same time, this number 4 is also not perfect. There are some holes, corrupted. Means the number 4 is actually missing. Some parts are missing. Now this one actually is different because I think the angle and the way it's written is different. And this one is actually shifted. Number 4 is there, but it's shifted to the bottom left-hand corner. And this is a nice 4, and this is your 4. Now, if you compare back to the patterns we had before, right? You can see, right? Of course, some of these actually are similar to the earlier ones. So, right. So I think the popularity or the one that actually make people sit up and pay notice, and people pay attention to his work is that because this number here is actually not in the training examples. You never train the network to recognize this number shifted to the bottom left-hand side. I suppose if you shift the same number to the top and the bottom here, it will still work. So this was one of the breakthroughs, if I may say so, of his neocognitron in 1988. So now that is actually we call generalization, right? We train the network with those seven images of the number four, and yet when you presented almost similar images patterns which are almost similar to the earlier ones, the one you know, it was able to extend, it was able to predict for you, even though it's never seen that number four shifted to the bottom left hand side before. So that is called generalization. So generalization, by definition, is the ability to recognize new data correctly without retraining. The keyword here is you do not need to retrain your system, right? And it was able to perform quite well, even though the system, the network has not seen this before. And you present the new data and it's able to recognize and tell this is number four, even though it's shifted to the bottom left-hand corner, or is with the number four itself is broken, right, in certain parts, not formed perfectly, and it's also sprayed with noise. Some of these defects, some of these uh, black spots onto the pattern itself. So it's able to learn it without you having to retrain the network and say this is still number four. So it gives you a lot of flexibility. You don't have to go back and retrain the network. Now, on the other hand, you have also adaptation. Now, what is adaptation? Adaptation is the ability to retrain, right? It means your network is able to retrain if necessary. That is because if the new data is too different from the previously seen. Now, let me give you an example. Let's say today I train you with, I train the network with only apples and oranges. So whenever I show you apples, the Washington apple, the what do you call it, the other types of apple, the green apple, and nowadays I think I've seen there's also yellow apple. I think yellow apple from China. But so your network is trained to recognize apples and oranges, even though I can show you different types of apples. But tomorrow I give you, so as long as you give me an apple, maybe the red is not purely red, mixture of red and green, or maybe red and yellow, my network can still uh, recognize correctly that this is an apple. But if I were to show the same train network with a strawberry, right? So you can also argue that strawberry is a smaller form of your apple because it's the same shape. Of course, it's it's a smaller, or because it's also red, but because it's a strawberry, actually it's not able to see it, right? It's not able to tell you that this is an apple. So in that case, you have to retrain. You start again. You train the third class, which is of strawberry as well, to tell it that this one is not an apple, neither is an orange, but it's a strawberry. So you have to retrain because the pattern itself is now too different from the previously seen fruit of apples. So that's your adaptation. So adaptation is needed when you need to retrain because it is very different from the patterns that you have been trained before, which is apples and oranges. Okay. Now, what are the implications? Neural networks are maturing. Neural what we mean, means that now I think many of you are working on it. So basically, I think you nowadays you see that the word neural networks is no longer restricted to just universities where the lecturers and the students work on neural networks. Now you see it in a daily newspaper, right? And neural networks can make, as a result, is actually people excited by it. I think some of you are actually working on neural networks to identify time series patterns. Means, for example, financial data. Right, some of you may be working on financial data, for example, the stock market prices, to predict, after learning it, to predict how the stock market will react given uh, certain factors that will influence its performance. So that's also useful because you can also make money. So if you can build a system which is very accurate, I can then use it as a financial advisor for customers. So I sell it my system and then of course you pay me, maybe for example, then again come back to your model, your business model, for me to for you to use as a customer to actually monitor your shares and tell you when to sell, when to buy. Right? This is what I call time series because it includes it actually involves a lot of numbers. So that is a usefulness in maturing. So other than that, can also be used in speech and voice recognition, recognizing who is talking, who is saying what, and also who said what. That is recognition, and what did he or they say? What did he or she said? For example, open the door. Um, please dial Danny's handphone number for me, right? Things like that. I think you've seen it in the I think the system that's sold by Google and I think a few other I think another company that such things are able to recognize. But of course, there's some what do you call the challenges because the whole world consists of various types of people. For Malaysians to speak English is a different the way we pronounce certain words compared to Americans. So that when you buy that system, you find that the system may not initially recognize your voice to say to for the commands you issue. Of course, you need to train it, right? So such things, speech and voice recognition, analyzing data in the past has been normally reserved for humans to do because your machines cannot do it yet. But now in the past maybe 10 years, you find that there's some the new networks have made some breakthrough. So therefore, it is getting very popular and mature, right? And computers, because the thing is that computers that could evolve because these are basically computing systems that can also evolve just like other forms of life. So in a way, this is quite exciting because your machine is no longer just static. Today, it will only recognizes apples and oranges, but tomorrow, with a sufficient training, it can also recognize strawberries and what do you call it, cherries, for example, things like that. And also we can do self-replication, can replicate, generate different what you call models, uh, expand, maybe scale up, by the process of self-replication. Now I'll go a little bit. I think this one I'll just very fast go through because I think many of you may be convinced that there's artificial neural networks is actually quite exciting and quite useful. So the main area application areas are in machine learning. For example, adaptability for fuzzy controllers, pattern recognition, yes, images, looking at uh, even things like patterns in a time series signal for machine monitoring, for stock market prediction, things like that, pattern recognition, regression, curve fitting. Uh, I did some work with a student, your senior last year, to actually look at trying to predict the quality of the river water. So he actually um, extended the work done the previous year by another student to actually design the system hardware through a series of lasers and what you call series of lasers and light meters to measure the light intensity of the water to tell it whether is it does it contain impurities. And then from that he actually use neural network to do curve fitting to tell me exactly based on this light intensity what is the expected or what is the predicted amount of impurities in that sample of water. Other than that, we have actually aerospace in the terms of high performance aircraft autopilots, flight path simulations, aircraft control systems, autopilot enhancement, aircraft component simulations, aircraft component fault detectors. In the area of automotive, right? Automobile automatic guidance system for maybe autonomous driving, warranty activity analyzers, and also closer to home, closer to our university, some of you may be working on to actually identify the defects of the wiper arms. So there's another area for us to look at. I think for some of you may be looking at other things. For example, it can be even things like car parts manufacture to identify the faults before they actually ship out to the customers. Banking, right? This actually, I think now we don't see much work in the universities on this anymore in terms of checking and for the signature of the automatic checking of the signature. so that I can also verify the check. Is it signed by the actual person or is it something different from that? And also credit application evaluators helping to evaluate if you want the bank loan, right? So are you credit worthy? Do you have enough money to pay me back later on? So this is what we call credit application evaluators using artificial neural networks. I think that a few other areas, defense, electronics, financial, manufacturing. So these are, I think, I won't go through this in detail. I'll just let you know that there's a wide field of applications of neural networks. It's up to you to imagine what you can do with it, right? So uh, some of you will be working in your project. I think what so far I have one student looking at using artificial neural networks to actually identify, or rather to estimate the ripeness of your palm oil fruit. And I think some of you actually will be working on this to extend the work in your FIP this year and for this year. Oh, then other areas will be medical, of course, breast cancer cell analysis, EEG, ECG analysis, robotics, speech securities, as I said before, market analysis, stock trading advisory systems, telecommunications, image and data compression, real-time translation of spoken language. This field is still pretty much open. Huh? I think this is real-time, yeah, and with a lot of background noise. So so it's also quite challenging. I think so far we don't have many students looking at this. I think that our expert here will be Dr. Hong to actually look at the speech and voice. Of course, it will be good. I mean, if we do it ourselves, no one else will do it in terms of looking at the English to Malay translation. Maybe even a big area we want Chinese to Malay translation. Why? Because as we Malaysia is a popular destination, especially with the durians. We have a Musang King and things like that for the Chinese tourists to come here. Now, imagine if you have create a application on your handphone to translate Chinese into Malay, so that the Chinese tourists shopping for durians, Musang King, can actually talk to the Malay sellers. So that would be I think, the interesting application. I have not seen um, much work being done in terms of Chinese to Malay translation, right? So in case you're interested, go and check it out and see whether there is actually such applications available. So it's just interesting because Chinese has a few billion people. Imagine even a small percentage of them become tourists, travel around the world, especially to Malaysia. Now, Malaysia, you have Malay. Then at the same time, what about Indonesian? Indonesian is a variation. Can I say variation? Or the two of them are almost similar. Of course, there's some differences in terms of how you pronounce certain words. But if you can do one for Malay, then you can do one for Indonesian. Now, again, what's the population of Indonesia? It's huge. So imagine the potential for the commercial success, the financial rewards of your system. Targeting only two countries, Malaysia, Indonesia. Big enough. Like I said, boleh makan. Transportation, looking at the truck brake diagnosis in case you tell the owner time to change your brakes because your brakes is no longer good enough, right? So things like that. Now, how what is the computational capability from the hardware perspective? How how powerful is your artificial neural network? So in terms of the ability to understand things, the brain, maybe in a simple way, talk in terms of the brain power. What's the brain what's the brain power of your artificial neural network compared to a worm, compared to something called aplysia, compared to a leech, right? Compared to a cockroach, compared to a bee, compared to a fly, for example. Of course, you can see where I'm coming from. So far here, I have not even let it compare against human beings because we are nowhere near. The artificial neural network is nowhere near your human being or your monkey. Now, this is actually done in 1989, long time ago. So this was the only study I managed to find. The look at the computational capability. in terms of the speed, the number of interconnections per second, how much you, I suppose, processor per second, and number of interconnects in terms of storage. So this is a 10 until 10 power 15. So the top here, the champion is your human. So this was done, this is quite a reputable study done in 1980, 89. So you can see here, the blue ones are your artificial neural network simulators. So they actually lies between the worm and the fly. That was in 1989. Probably this has moved a bit in terms of the ability of your artificial neural network simulators here, especially with the introduction of your deep learning neural networks. But so far, it's only comparing to the lower life forms, your worm, your leech, your cockroach, or your bee, right? So it's somewhere down here, just to give you a taste of where the simulators stand. So it's a far cry, it's a long way from competing with human. But of course, this is in terms of measuring in terms of speed and also the storage, not in terms of the capability to recognize images. So again, that is a different story. Now, I'll quickly run through this to give you a appreciation of the history and some of the key people that has contributed to the field. These are the key people that contributed. Of course, there will be many others, right? Equally important. But again, my intention is not to show you everything, but to show you a slice of the major contributors and what do they bring to the table? What have they contributed that make their work so significant? So these are the measurement of the milestones. So the first one was actually in 1943, where McCulloch and Pitts they actually model the fundamental brain cell, that is the neuron. They actually model it in terms of mathematical representation of your neuron. It was in 1943. Then a few years later, in 1949, Donald suggested a model for dynamic memory. So this is a learning algorithm to train your network. So this is for dynamic memory in 1949. Then maybe another 13 years later, a major uh, development occurred. That was by Frank Rosenblatt. That he actually built a early vision system using the McCulloch-Pitts neuron. So this is artificial neural network that can recognize things, recognize images. So this is an early vision system by Frank Rosenblatt. Then Minsky and Papert, I think this one, if you look at the history of neural networks, you find that this is actually a major milestone because Professor Minsky and Papert actually challenge the work done so far. What they are saying is that the neural networks is rubbish. Actually, it doesn't work. It's only good for certain toy problems. It's not good enough for serious problems that we have in the world. So they because of their reputation, uh, people respect them. Of their respect, people respect what they say. So as a result, they basically kill the neural network research in 1969. So that's why I show a picture of a nuclear bomb exploding. So actually, they are they are they are they are actually they are as a result of their what I call their recommendation, right? Has a very serious effect because in those days, I mean even now, research has to be funded. Someone got to give money. So in America, the major funders are the government. So if the government believes that uh, and and respected Minsky and Pepper. They respected their what they say, and if they respect and believe them, they say, okay. As a result, I will no longer fund you. I will give money for any research on neural networks. So what does it mean? It means your lecturers will no longer propose any research into uh, neural networks. Say, for example, right, back to closer to home now. Imagine that being said now. If we say that as a result, Malaysian government will not fund any projects with the title deep learning, for example. What that means? It means your lecturers will not will not attempt to propose projects based on deep learning. So as a result, it has a serious implication on the on the health of neural networks research in 1969. So it took a long while. In about 13 years later, when Professor John Hopfield, as I said before, he has a significant contribution. He was the one who said that he provided mathematical analysis, which paves the way for the revival of artificial neural networks research. So he waited for 13 years before someone came along by the name of John Hopfield, said that, hey, wait, it's not as bad as you think. Neural networks, I can show you, it still works. So as a result of that, it actually bring back from the dead, bring back from the dead the research in neural networks until today. That's why I think those about 13 years, I think no one touch neural networks because there's no money. No one will provide money to do your work. So let's go in a bit more detail, a bit more detail of the history of neural networks. So as I said before, in 1943, Macaulay and Pitts, and they make the first mathematical model of the artificial neuron. So you can see 1943, a long time ago, right? More than 50 years ago, uh, started from there, right? The base is based on the idea that neurons operate in an all or some fashion. That was their mathematical model of the neurons. And Donald Hebb is the one to talk about the learning algorithm, how you train your networks, right? So he's the one that's famous for Hebbian learning. I think later on we'll come across this again. So the basically is the talk about the efficiency of your synapse increases if there is a pre-synaptic activity to follow. That was what is basically the idea behind his Hebbian learning, named after him, right? The learning method named after him. Yeah, this is Minsky and Papert, right? He's Seymour Papert actually looks at and kill off interest in this area for many years, right? So he felt that Rosenblatt actually was talking nonsense, right? There's no data, right? No data to show that the perceptron actually works. Right? So he killed off the research in that area or interest in the area for many years. I think I showed before, 13 years. So then in 64, there's another piece of interesting work by Stephen Grossberg and his partner, Gail Carpenter. She's one of the few very famous researchers in neural networks, right? So uh, you can see her work actually was on nerve impulse, very mathematical. So they are actually quite influential in their work. So if someone said that I'm working on neural networks, the person should at least uh, be able to tell you that if you say the name Grossberg and Carpenter, he will say, yes, I know, I've heard of them, right? Because their work is actually quite very influential and it's actually renowned, famous as a thorough artificial neural network researcher and a lot of mathematics behind it. So you can see here, they provide a lot of rigorous, strict mathematical analysis, right? Of self-organization, self-stabilization, and self-scaling, right? Maybe to look at even things like convergence for that. Ah, Closer to Asia, of course, these are all the Westerners, and then closer to Asia, there are a few key people. One of them is Sunichi Amari, Professor Amari, in 1967. He actually conducted substantial research on artificial neural network theory. He combines biological aspects with rigorous mathematical analysis. So you can sense that in order to do well, to be as famous as them, you need to have a strong foundation in mathematics. And he actually provided the rigorous mathematical analysis. I met him a couple of years ago in, I think, mid 2000 in one of the conferences, and actually being such a famous person, right? He has very modest. He can still laugh with you, talk to you. You don't have to call him a Dato or whatever. So he is approachable. Basically, what I'm trying to say, approachable. So this is one of those things. Sunichi Amari, and then the other one, of course, is a good friend of his, Kuni, Kunihiko Fukushima. Fukushima, 1969. I think they are about. They should know each other because they actually the work is around the same time span. He studied spatial and spatial temporal, space and time, artificial neural networks models of the visual system and the brain. So he actually studied from there, got the inspiration to actually build his neocornetron. Now, reputed to have created the multi-layered neural network, the non-connectron. You can see here. You see here, he's actually known to have created a multi-layered neural network as many as 9 layers. I think to many of us now, 9 layers is considered a deep network already, as maybe the lower end of the deep network, which is a neoconnectron, right? And to recognize things, as I showed just now, the number 4. So you have a neoconnectron able to recognize distorted, shifted, rotated, and even scaled handwritten numerals, right? So maybe nowadays you find that, there's nothing. But those days, 1969, when the computing power is not so great, imagine you have to train 9 layers. You know how much effort you need to do that to train it, right? So actually, he's also a well-respected researcher in the field, especially from Asia. So you can see here, uh, these are the only two, I think, only two Asians researchers, well-known Asian researchers in the field that has contributed a lot to the artificial neural networks. And also, you can see here, um, of course, I think now if you look at the work, the papers published on deep learning, I think you hardly see his name. But actually, if you look at the history, you find that he was actually the early developers of deep learning or deep neural networks. He was considered quite deep, but of course lower end of the deep 9 layers. Of course, nowadays you have hundreds of layers in that sense. Ivo Konen, he's a European. I think Helsinki is in Norway, I believe. Professor, he's looking at basically associative memories, and then he look at basically his original contribution is actually the LVQ, which is a learning vector quantization. So the LVQ can automatically, without any supervision, you don't need to train the system to tell what it's supposed to learn or do, and determine the k best reference vectors from a sufficiently large set of data points in n-dimensional space. His other contribution is also the self-organizing maps, and he's written 3 books on associative memories, and retired in 1999. Reference Sternovsky, 1976. Again, this as you can see, Professor Sternovsky, another well-known name with a strong background in mathematics as well as biology. He actually developed the Boltzmann machine algorithm with Ackley and Hinton, and his extensive work in applying backpropagation to map text to phenomic representation. So basically, his thesis into to map the basically is a text to speech. So if I can, if you present the uh, document, a series of text here, his system should be able to read out for you how to pronounce the word biology, co-discovered, things like that, right? And he applied the backpropagation algorithm to classify sonar signals, right? That is from the signals from using the sonar to actually ping the sea, the oceans, to recognize objects, to recognize animals in the sea. And the results were even better than human effort. So you can see even as far back as 1976, there was some significant developments, breakthrough in the field of artificial networks, and actually the results were even better than the humans. Eklund in 1977, they are actually psychologists. They are actually cognitive psychology background, but their main interest is to use artificial neural networks to help understand the function of the mind. How does the mind works, right? So imagine if you can build an artificial mind, right? Then you can actually look at it to see what is wrong with the human uh, state. For some humans who suffer from psychological uh, problems. So you can, instead of how you probe human mind. So this one actually is a model of the human mind. And actually, they produce 2 very well-known books. Actually, I bought the 2 books, but actually, after buying it, I didn't read it. I didn't have time to read it. But of course, it's no excuse, but it's a good book, a very well-known book, Parallel Distributed Processing, Exploration in the Microstructure of Cognition. They also look at speech models, physiology of the brain, and also mathematical analysis. Bevel and Ballard, 1980, and then they look at the different models of your neural networks to look at semantic networks for natural language, logical inference, and concept representation. Hopfield and Tang. So I need to spend some time looking at this. Hopfield, together with his partner, David Tang, they actually discovered significant application of neural networks, and they actually look at the methods to analyze the stable points within a neural network. Where are the stable points? As you'll see later on, I think we'll discuss this in the next lecture on Hopfield nets. They actually spend some time to do some mathematical analysis based on the Lyapunov energy model. Now, surprise, surprise, he is not a mathematician. He's actually a uh, I think, biologist. Right? I'll show later on. He's biologist. So you can see, it doesn't mean that you are engineer, you cannot be good at, say, biology. For a biologist, he's actually very good at mathematics. Then he actually extended the Lyapunov energy concept to spatial temporal pattern storage and temporal speech pattern recognition. I think in the part of about 10 years ago, I spotted, I come across his papers looking at trying to model the human nose to smell, to tell you what is the smell of a certain substance. So he was doing that artificial nose, if I'm not mistaken, about 10 years ago. So far, I think he's probably retired. So I didn't see any work being published so far. Bart Costco, he's the one to talk about the bidirectional associative memories and also combine fuzzy logic and artificial neural networks. There was his three significant contributions. He combined fuzzy logic with artificial neural networks. Robert Hartnell, he's one of them who actually I come across, actually founded a company to actually do neural computing, right? That was in 79, right? And then he's actually developed the hardware, the neural computers in those days. But I think you can see, I think there's nowadays I don't need that neural computer. I can just buy any extra processors to actually speed up my processing. Okay, so that was the part on the history, short history of the history of artificial neural network. Okay, are there any questions so far? So looking at the time, I think I should not start on the perceptron. Because I start on the perceptron, I will basically have to come back again. Right? So I'll stop here, and then we will continue in the this Friday. This Friday I will continue. Okay, I stop my recording. Okay, are there any questions? Yes, Christopher, questions? No? Okay, good. Okay, welcome, Can find. Uh, so I think looking at the situation in the country, hopefully things are changing to be better. And I hope that all of you can have a chance to actually have your vaccination so we can meet each other in the campus and not through these online sessions. Okay, so I'll stop here. I'll stay here for a while in case there are any questions from any of you. Right, bye-bye.
Thank you, sir.
Well, you're welcome.